Today I will talk about the utilizing flooded coal mines for extracting energy for heating and cooling applications. My name is Professor Amin Al-Habaibeh. I'm Professor of Intelligent Engineering Systems at Nottingham Trent University. I'm also the Director of Product Innovation Center, and we do a wide range of applications in relation to energy, sustainability, renewable energy, and as well as medical applications and other technology as part of the Product Innovation Center. I'll just talk about the technology of how we could extract energy from flooded coal mines and some case studies of the work we have done, and hopefully we'll conclude with challenges and opportunities of using the technology. So this work supported by Innovate UK, KTP project, and the European Commission and Alkane Energy, one of our company partners on the project. So coal mines, this is a classic coal mine in Europe, and you can see the space sort of cavities. Once these mines are, there's no more sort of, they are not any longer operational. Normally they have a space. That space sometimes could be filled with methane that could be extracted to generate, again, energy or extracted for use. But over time, they get flooded with water, and this water normally at regulated temperature. So if you look at from the Industrial Revolution time, we have extracted in the UK almost 12 billion tons of coal to use it for energy. And that means simply we have significant space voids underground. We have, and if we assume 10% space, almost we have 1 billion cubic meter basically of space voids underground. And these are normally filled with water at 14 degrees because of the weather in the UK and the water table. So it is so there is an advantage of using that water for heating and cooling applications. So in the UK, even already we pump about 112 million megaliter per annum of water. Basically to keep to treat water and to keep some areas safe, and that's equivalent to more than 44,000 Olympic swimming pool of water. So there is already, we pump water and we already use water. Now if you look at the temperature of the water is very stable at about, in most cases, 12 to 14 degrees. While if you look at the blue line, the weather conditions in winter is cold, in summer is hot. But the water underground is very constant, which we could use then directly for cooling or through heat pumps for heating and cooling applications. So this is how it works normally, and this is one of the systems we've used. So we pump the water from the coal mine to a heat exchanger, and we return the water back if it's cooled through the heat pump, through the heat exchanger back to the seams, and then that heat basically through the clean sort of side, as it were, of the system, we take that heat and use it for heating water. And we are familiar with the geothermal heating, whether we have the sort of, but most of them, those systems are closed loop systems. That means we circulate the liquid and we need time to exchange heat with the ground. But with the advantage of flooded coal mines, actually we can pump the water directly. We don't need a loop, closed loop. We can pump the water, get the heat, and then, or the coldness out of the water and release it back to the ground. And then becomes much more, has got more capacity. And just for people who are not aware of the heat pump as a concept, it's very similar to a fridge in your kitchen. Basically, the inside of the fridge is the cold side, and normally at the back of the fridge there is basically the hot side or the condenser. And so if you put let's say a hot water bottle in your fridge, it becomes colder because the heat actually extracted from the bottle to the outside the fridge. So you'll find the external side of the fridge is hot. And this is a heat pump in simple terms. And we use it normally so that we can, so imagine the water inside the coal mine is the water we put inside the fridge, and then we can take the heat from outside the fridge and heat the building with. And we get more energy than what we use in electricity. Heat pumps use electricity, but we can get more energy from that. That does not contradict with conservation of energy concepts. It's because we actually take the heat from the water through the electricity. So if we have 7 kilowatt of electricity, we extract the heat from water and we could get 28 kilowatt of heat. So an electric heater, for every 1 kilowatt of electricity, we get 1 kilowatt of heat. With the heat pump, you can get more than that, double that or triple or more than that due to the process of extracting the heat from a specific media like underground heat or the coal mine water. So there are already systems in place heating the buildings. One in Heerlen in Holland. You can see I like my selfies there. So the advantage of the system is actually when you visit the place, you don't see it because it's a simple container on the underground level. So there is just a park, and suddenly you go and you enter that container. Suddenly you have all the pumps, the heat exchangers, and basically without anybody noticing, there's no noise, there is nothing. And suddenly you have actually a very efficient heating system for local community. This is another one in Asturias in Spain, very well. And again, the heat exchangers take the heat from the well, and then the heat transferred in a closed loop 2 kilometers away to a university building and hospital. And it's been running for a few years now. It's very successful. So our research in the UK, we have two sites we've done the work on. One in Cap House in the National Coal Mining Museum, south of Yorkshire, and one in Markham Junction 29 of the M1. This is the satellite site of the Alkane Energy site where we've done the Markham Vale sort of location. And so what you see here, you have two gas engines and a small green container there. So this is actually the heat pump. These company buildings, and these are the gas engines that use gas to generate electricity at peak times. And this is here the shaft where the coal mine shaft is. So another picture. So these are gas engines, the mine shaft, and the container which has the heat pump. And this is the schematic diagram of the implementation. So we pump the water from the shaft of the coal mine to a heat exchanger and back again. And then basically this is the rest of that is a clean cycle, closed loop of taking the heat through the heat pump to a buffer tank and basically to the building. And that buffer tank basically is to, when there is no demand for heat, you can store significant amount of heat. And we'll come to this in a bit because we actually use that also in more efficient way. And you can see the system in a container. And if you wish to keep it within underground level, you can do that without any problem. This is an infrared thermography of the water. So the water basically comes. You can see the water how it is warm coming from the ground and is leaving at lower temperature as well. So and that's the difference in the delta T is what we use for heating through the heat pump. And this is the seams of the Bolsover colliery and Markham collieries as well. So this is what you see and what's underground, and this is the shaft we are using. The rest are closed because it's no longer being used. It's a closed mine, but this one is what we are using underground to extract the water. And you can see here basically we take the water to the heat pump and deposit again at a different level. And what we found is that during 80 days, for example, that time the temperature was about between 14 and 13 degrees C of the water, even with the operation of the system. So it's very, very constant temperature. And the COP, coefficient of performance, which is how much energy I get over how much energy I spend. You can see here for the heat pump, it's very high. It's above 3.5, but the full system was above 1.5. That means for every 1 kilowatt of electricity you use, you get 50% extra of heat. Of course, that's because of the depth of the water, because we've got to pump the water from a specific depth. Now, with time, that depth of water goes up with time because of the rain, and until it reaches the water table. So what happens is it becomes more efficient over time, and then you spend more electricity on pumping the water, and then the system becomes more and more efficient. And this is a diagram that shows if the water depth is 25 meters, you can get actually COP of the system of 4. That means every 1 kilowatt of electricity you spend, you get 4 of heat. So it is very, very efficient technology. And in terms of the mine water, if it's away from oxygen, we will not have oxidation. So that becomes, again, after 2 years of operation, not much ochre happened in that site. And also what we've done, we went beyond actually the water from the flooded coal mine. And if you look at the electricity grid in the UK, there is a specific time in the evening where there is high demand when people come home to do cooking, have showers, and suddenly you have a peak of electricity demand. And the gas boilers on the site, actually they are on standby so that they can top up the grid with electricity, and they produce heat. So what we've done from that heat, the waste heat from the engine, we've connected that to the buffer tank, which you've seen previously. And then in some cases, that heat alone could heat the building. So we could attach it to the buffer tank and heat the building. And that made the system even much more efficient. The second site is Nottingham Coal Mining Museum. That was a different story, because if you visit there, that's actually a museum, and it's a free museum. I advise everyone to go and visit. They actually they pump the water from the museum, because you can go underground and see the galleries. So again, I advise everyone to visit the place. They have these orange ochre ponds because they treat the water they pump from underground before it goes to the river. So this is the satellite image of the ochre pond. So if you go to Google Map and search for National Coal Mining Museum, you should be able to see these ochre pond, which is basically for treating the mine water. And this is in man building, where basically we've had the system, the heat pump system, where we basically had another technique where we took the water out of through the system to heat this building. And this was slightly different because the water was already pumped from underground to the lagoon for treatment. So all what we've done is actually take one part of the water or a portion of the water to our heat pump system, and again heat the building with. This was a slightly different story because the water quality is completely different from Markham Vale. This shows again the content of the heat exchangers, the filters, and the heat pump and the buffer tank of the system. So to finalize, in relation to pathway to commercialization, there are a lot of opportunities reflecting on these systems. They are support net zero strategies, are very efficient, very stable. So if it's very cold outside, the water is still warm to be used. And if it's in summer, you can use the water directly for cooling, because it will be at 13 degrees. So it's a very, very efficient system to use, and could save significant energy and on carbon emission and money as well. But there are some challenges. For example, it's not well understood to people, the investors, to the developers, when they build the new houses, they don't know the legal issues involved. Some people don't understand the technology. They don't know the long-term issues. They don't know how people would change suppliers. So there are still some challenges about how people could use the technology. But what we found in relation to the other case studies, that if you have one customer who needs the energy, like a hospital or a university, that becomes a simpler way to implement the technology. So issues to consider further: there is a need to develop clear models and case studies, so that similar to the ones in Spain and Peredo, to encourage people to adopt the technology. The cost of infrastructure sometimes could be very high. depending on what's the situation of the flooded coal mine and so on. So there could be capital investment at the beginning. So again, we need to convince people or developers about adopting this technology, and also convince the customers and users to use it. So in the short term, we could utilize this technology in a very simple way. If we have already infrastructure, borehole is available, water already pumped, for example, government organization can absorb the cost of infrastructure if needed, or if possible, and one user to use the technology, the energy, such as hospital, university, or shopping mall, and so on. So that becomes a very simpler way to use it. But in the long term, we need to integrate the technology with education. We need to have public engagement, public awareness of the technology, so that they can be aware of that. And what's nice about the areas where the people have the coal mines, there is still a culture and heritage of the coal mines culture. So people really very keen to have that coal mine back again to their daily life, from grandfather's time or father's time to become sort of their future as well. So there is the cultural issue as well in relation to that. And also in terms of education, public engagement, this is a simple simulator I built with my students to simulate how the technology works. And in a simple way, we use a fish tank and a small fridge, car fridge, or cooler, drink cooler. And actually, we showed that a small radiator can actually become warm. And there is a paper on this published as well. So if you want to have a look at this one. So this shows how the technology is so simple to be done. And actually, you can use it for heating. So thank you very much for your time. This is a QR code of my LinkedIn. Please feel free to scan it and connect with me, and hopefully we could develop further collaboration. Thank you very much indeed.